Okay, so even if we don't use this generalized view, okay, let's erase the box and let's just look at more traditional picture. So all the current flowing here, they have to go into either path 1 or path 2, and path 1 and path 2 will recombine at the second node. So you apply KCL twice. You don't have to solve the individual component. You still get the same equation. Okay. So current gain, IS, current gain is equal to I out divided by IS. They are the same, other than the direction is opposite due to our definition of I out direction. So it's -1. Okay. So it's a unity gain, current gain device. Yes.
So what determined that we defined I out looking in? Or was that just?
It's just a convention. We stick to the convention and we define the voltage according to this convention. We could have defined the convention the opposite way. The arrow, remember, arrow doesn't represent the real current flow direction. It's just what we call positive. Okay, all right.
And then for the equivalent node, is that, I mean, even if we have an active source supply there,
Yeah.
according to KCL, we will also get this AI equal to -1, right?
Yes, yes, yes. So doesn't matter how the current is distributed among these two elements, these two branch, they will all sum up to be the same. The totals remain the same. So unity current gain. So there is maybe your first question. Why do we need it? It doesn't amplify the current. Why do we need it? Well, these are so-called current buffer. Remember, we talk about voltage buffer. Why do we need voltage buffer? Remember, anybody?
For loading.
For loading. So you transform something with maybe high input impedance to low output impedance. So it's kind of providing an impedance matching. So here, let's look at input impedance and output impedance. This is maybe give us a clue. So input resistance. Okay, input resistance, we said we need to attach RL. So we move RL back here, and we basically put the test voltage source here. So we apply VT here, okay? Doesn't matter, we call it VT or VX. And then we try to solve KCL, KVL, try to find the relationship between VT and IT, okay? This circuit, well, you can see they are, you can basically collapse these two resistors here, RD and RL. These both are connected to ground. So you can kind of write them as, let's call R prime equal to RD in parallel with RL. So we basically replace them with just one resistor. And this node is V out. This node is VT. This node is V out. So if we apply a KCL here, so KCL at node 1 at 1. So you'll see IT is equal to this branch, IT going in here. Now GMVS is going in also. So this should be minus GM VGS, okay, plus the current going out. So this path is VT minus V out, VT minus V out divided by R0, okay. Now we need to eliminate all the intermediate variables. GM is a known parameter. VGS, what is VGS? Well, gate is grounded. Gate is grounded. So VGS is equal to 0 minus VT. So VGS is minus VT. So this term become GM times VT. Okay, we eliminated one intermediate variables. Vout, well, Vout we know all the current must flow through the combined resistor in parallel. So we also know Vout is equal to VIT flowing through RL in parallel with RD, right? So that would be the voltage at the output. Okay. It will be a little bit clear if I replace the two circuits. So if I redraw the equivalent circuit here, okay, and this is my test voltage, and here is my R prime equal to RD in parallel with RL. Okay. So if I redraw the circuit like this, then your output, so here is IT, right? And we say IT will continue to flow here, so IT will flow down here, and the voltage drop, V out, is basically the current times resistor value. So we have V out here. So I substitute this back here, and well, let me erase this here. So basically, VGS equal to 0 minus VT, and this substitute in there, then you'll get IT equal GM VT plus VT divided by R0 minus V out is this guy, IT times RL parallel RD divided by R0. So this equation has only IT and VT. So you just take VT. Yeah. So R in, basically R in is equal to VT divided by IT. Okay. The equation may be complicated, but you can solve it. Let's say. So this is the, let's trace it here. Let's trace this equation. Let's write it here. So VT divided by IT, VT terms are GM plus 1 over R0, and the IT terms are 1 plus RL parallel RD over R0. Okay, so that comes straight from this equation here. Okay, simple algebra. So now here they are looking at inverse of R in. It's actually not necessary. These are exactly same equation here. So here is what comes handy. Circuit, when we do hand analysis, remember, we usually are happy just to get 10% accuracies. We want to know the function of the circuit. The point is not to get accuracies. So accuracies, you get it from Cadence or from SPICE, from more sophisticated simulator. You get temperature dependence, you get many other things that are impossible to do by hand. So by hand, you would just want to know what's the function. Okay, so we can throw away terms. If you know what terms to throw away, it makes your life a lot easier. Okay, and we'll see why. So here comes in the typical orders of magnitude. So GM, we say GM is, we haven't said what's the typical value for GM. GM is usually half millisiemens Siemens is M divided by volt. Okay, so GM has a unit of M divided by volt. Milli means 10 to the minus 3. Okay, typical number. R0, we said typically about 200 kilo ohm. Okay. So here, let's see, comparing the two terms. Let's flip it. Okay, let's look at this equation. GM, so this is 0.4 times 10 to the minus 4. Okay, 5 times 10 to the minus 4 for the typical value here. And this 1 over R0 is 5 times 10 to the minus 6, right? So this term is way smaller. So you drop this term. Okay. And what about RD and RL? Well, RD, if we use RD, RD is typically a few kilo ohm. Okay. So a few kilo ohm. Obviously, this depends on your design, your biocircuit design. But remember, the current flowing through there is on the order of milliamp. So you cannot have 100 kilo ohm as your RD. You know, the voltage drop there, it blows up. 100 volt. You don't have 100 volt power supply. So it cannot be that high. So it has to be on the order of a few kilo ohm. RL, well, that's the load. We don't know what is RL, right? We don't know. But typically, they are also not very large. And if you have RD and RL, you know RD, so here, you don't quite know. So this you really, you can keep the term. If you don't really know, you can keep the term, okay? But we do know R0 is large, and it's likely whatever their ratio to R0 is also small. So you can also kind of drop this term, okay? You drop these two terms. So you get R in, if you look at this upper equation here, you get R in. If you drop these two terms, you get R in equal 1 over GM. So GM is transconductance. 1 over GM has the unit of resistance. 1 over GM, if we use this example, it's 2 kilo ohm. So the typical number suggests it's 2 kilo ohm. Okay. So in the hierarchy of resistance, 2 kilo ohm, these are kind of considered a small resistance. Okay. So whenever you see 1 over GM, it's small. Well, whenever you see R0, it's large. Okay. And whenever you are comparing either, so R0 is much, much greater than 1 over GM in terms of resistance, or you can say the opposite. GM is much, much greater than 1 over R0. Whenever you see these two terms, it's very safe to omit the smaller term. It's 100 times smaller. Okay, so that simplifies your expression. It also tells us common gate amplifier has low Rin, has low input impedance. That's very important. So let's look at output impedance. So if it is doing impedance transformation, it must have very large output impedance. Okay, so let's see whether this is the case. For output impedance, we leave the source resistance in, so we put RS back in here. We replace the load with a test voltage, okay? And we have RD here, okay? This RD is for a current source. This RD really is a shunting resistance. So I can further simplify my analysis. Let's temporarily take out RD. What do we mean by temporarily remove RD? Okay, we kind of cut open here for now. When we find our output resistance, we put RD back in parallel with whatever we found. So whatever we found are from the rest of the circuit. Okay. Now taking out that branch makes our analysis much simpler with no impact in the accuracy. So, okay, so we have IT and we have VT here. So this node is VT. And we can do a KCL here. So KCL, okay, KCL at this node, basically this line, they are all the same node. The current going out to the resistor is Vs. So this terminal is Vs. Vs divided by Rs. So that's the current going this way. Okay, Vs divided by Rs. And current going in, that's a GM, VGS. And current going through R0, that's Vs minus Vt, Vs here, minus Vt divided by R0. So that's our KCL here. And you group the terms. VGS is simply equal to 0 minus Vs. Okay. So we can replace the term here. We have Vs. All the terms either have Vs or Vt. Okay. Vs. Okay. Now Vs from here we also know Vs is basically equal to the current. Now this is the same as before. All the current coming out here, IT, if we take out that RD, all the current have to end up here. So the current flowing through the resistor is precisely IT. So Vs is basically IT times Rs. So you replace this Vs by IT times Rs. Now you have only Vt and IT. So you can calculate the output resistance. So ITRS, and this is Vt, okay? So you calculate Vt divided by IT. So this is equal to Vt, so this is Rs, R0. Here is, well, let's just multiply it. Let's just multiply it out. Okay. So Vt is equal to IT times, we multiply both R0 and Rs. So this becomes R0 plus GM, R0, Rs plus Rs, right? So R out, this is actually R out prime. It hasn't included the RD yet. So let's call this R out prime. Vt divided by IT, this is equal to R0 plus GM, R0 Rs plus Rs. Okay, so now here we can use our typical number again. But before we simplify, so we need to put back RD. And if we look at this diagram here again, what we find, the R out prime is really here. Everything included here, we look in here, we find R out prime, right? So R out prime is in parallel with RD. So we finally just put RD back. It's RD in parallel with this expression. Okay. Now we can simplify again. So again, look at the typical number. Okay, here, actually, I have a typical number here. So GM, 0.5 millisiemens or 500 microsiemens, roughly the same. RO, think about 200 kilo ohm. Okay, so GM-RO, the product of the two fundamental parameters of a transistor, what's the value GM-RO here? GM-RO will be roughly 100. Is exactly 100. Okay, so this is 100 Rs plus Rs. Okay, so hand analysis, you say, I'm going to drop RS. I'm going to drop this term. Okay, you say, hey, that's 1%. Remember, 10% is good enough. 1%, you'll happily throw it away. Okay, so you throw away R0. You can almost throw away this R0 term as well. Okay, but we don't know what is this RS value. So, well, let's keep it here. Let's keep it here. Let's keep here. So our output will be RD in parallel with this term here. But the second term is likely to be much bigger than the first term. Okay. And now, since they are in parallel, we mentioned RD is likely to be a few kilo ohm. So the likely resistance here is likely to be just RD. Right? All this big output impedance is overwhelming. Okay. On the other hand, you can design a circuit. Let's say if we design a circuit that has a current bias instead of RD. So if I design a circuit where the output port is biased by a current source, okay, this is actually a possible circuit. I make these two current sources the same. I have a current source driving the source. I have current source driving the drain. I apply my input here, just like before. I take my output here, right? Now the equivalent RD, so the equivalent RD here is infinity. If I have an ideal current source, you look into ideal current source, AC is open circuit. So RD is infinity. So if I have a real resistor, my output resistor is limited by RD. But if I have a current source load, okay, if I have a current source load, which is equivalent to saying RD is infinity, in that case, my Rout remain very large. My Rout will be R0 plus GM R0 times RS. This is a very large resistance, minimum 200 kilo ohm, and this product is likely to be much bigger than 200 kilo ohm. So output resistance is large. Okay, so this has large Rout. Okay, previously we say it has a small Rin. So it's a current buffer that has a small resistance that lets whatever your signal comes in, it sees a small resistance. Then make it into an ideal current source that has a very large output resistance. So we now have this two-pole model. Okay, so the common gate, if we model it as a two-pole model, this two-pole model is not to be confused with the small signal pi model of a transistor itself. This is the whole circuit. The whole circuit, we look in, this is Rin. Rin is 1 over Gm. And I have a current gain. For current output stage, I should have Norton configuration. So my Rout is in parallel with my dependent current source. My dependent current source, AI, is equal to -1. Okay, so that's the whole circuit. Okay, and it's a current buffer, no current gain. Buffer means no gain, same current, but I provide the impedance transformation. I transform low input impedance to something with a high output impedance. Okay. Impedance transformation is almost as important as providing gain, either current or voltage. Any question here? So we go through a very detailed analysis of this kind of exotic configuration. And as we work more and more on it, you'll find it's not exotic. It's very commonly used.
What is the common value for the saturation current of the transistor?
Common value, again, common value, you can think roughly on the order of, say, fraction of a milliamp. So IDS, typically is a discrete transistor like you are doing in your lab. It's typically a milliamp. For integrated circuit, they are typically smaller, maybe 0.1 milliamp to 0.5 milliamp. Okay. So here's an open question. So we have that common gate. If we use this common gate as an amplifier, as a voltage amplifier, so it has a voltage. It has a voltage. It has a voltage gain. So if we use V in here, and I will have a V out, I can calculate the voltage gain of this amplifier, right? So we already know the current gain is -1. What about voltage gain? We don't have to analyze the circuit again. We can go to the circuit we already found. We already found 3 fundamental parameters. We can derive everything else from these 3 fundamental parameters. So let's reproduce that here. So the 2-port model, the resistance is 1 over Gm. Okay, I have a dependent current source. Okay, and the value of the source is minus I in. Okay, so here's I in, minus I in, and I have a very large R out here. Okay. And now if I attach a voltage source, okay, so I attach a voltage source here, V in, okay, and I want to know what is my V out. I don't attach any additional load resistance. So this is how I utilize the 2-port model I already found to solve additional parameter that we did not do the small signal model with. So here, I in is very easy to find. It's simply V in divided by the input resistance, which is 1 over Gm, or is equal to Gm V in, okay? And V out is simply this current, okay, multiplied by R out. So V out is simply the current, which is minus V in times R out. Now the convention is plus to minus, so I need to add another minus sign here. So this simply equal to I in times R out. And I in, I substitute this here. This is Gm R out times V in. So in other words, my voltage gain is equal to Gm R out. Okay, Gm R out. Now, if I have RD, here, okay, so if we have RD load rather than current source, so instead of current source, then we say, well, that R out is mostly likely it's equal to RD in parallel with something really, really big. It's approximately RD. In this case, AV is equal to Gm times RD. Does it ring a bell? Gm times RD? Have you seen it before? Gm times RD. Looks familiar? Let's go way back. In the very short examples we've done here, the common source, the one that we are most familiar with, the common source example here. The gain is GM, well, I have RO. Okay, so if I have a load, if I use a load here, RD, okay, and this will be, if I connect RD here, RD will be here, the AV will become minus GM R0 parallel RD, okay, and again, R0 is most likely much greater than RD, so voltage gain here is minus GM RD. So common source gain, GM RD. The common gate that we just solved, the AV for this guy is GM RD in case I have RD bias here. So they have the same gain. They have the same gain. But common source, what's the current gain for common source?
Well, for common source.
For this guy, upper configuration, common source. What is the current gain? AI? What's the current gain? You can find it by just looking. That's why I'm asking you. You don't need to draw small signal model. Huh? It's one? Not this one. This one we say current gain is minus one.
Oh,
the top one, this one, the common source. What's the current gain for common source? 0. Well, current going in is 0, but we are measuring output versus input. Infinity, yeah. So this current gain is infinity. Even though they have the same voltage gain, their current gain is kind of totally opposite. This is because their input-output resistance are totally different. Okay, so if we do a mini summary here, okay, for these two, let's jump to the summary. We'll come back do common drain later. Yeah, well, too much jumping. We'll just do that next time. So, so far, take-home lesson today, we look at common gate in detail. Common gate has low input resistance, very high output resistance, and unity current gain, and medium voltage gain, just like common source amplifier. Okay, all right, we'll stop here.